In this video, we're going to be talking about the analysis of categorical data and the goodness of fit tests, specifically the chi-square test for univariate data. Now, suppose that we wanted to determine if the proportions for the different colors in a large bag of M&M candies matches the proportion that the company claims is in their candies. Well, we could record the color of each candy in the bag. This would be univariate, or categorical data. So how many categories for color would there be? Well, there are 6 colors of M&Ms, so we would have 6. So here K equals 6, and K is used to denote the number of categories for a categorical variable. Now we could count how many candies of each color are in the bag. So let's say that we had 23 red, 28 blue, 21 green, 19 yellow, 22 orange, and 25 brown. A one-way frequency table is used to display the observed counts for the K categories. Now, a goodness of fit test will allow us to determine if these observed counts are consistent with what we expect to have. So here, our null hypothesis. So a goodness of fit test is used to analyze univariate categorical data from a single sample. So our hypothesis test would give us a null hypothesis that, let's say our P sub 1 equals the hypothesized proportion for category 1. So P sub 2 would be the hypothesized proportion for category 2, all the way down to P sub K, where P sub K is the hypothesized proportion for category K. And then your alternative hypothesis, or your H sub A, is that your null hypothesis is not true. So H sub O is not true, or H sub naught is not true. The test statistic is x squared, and it's going to be the sum of the observed cell count minus the expected cell count quantity squared divided by the expected cell count. X squared is actually read as chi squared. The x squared value can never be negative. The goodness of fit statistic, denoted by our x squared or our chi squared, is a quantitative measure to the extent to which the observed counts differ from those expected when our null hypothesis is true. Now, as far as p-values goes, when our null hypothesis is true and all expected counts are at least 5, our chi-squared has approximately a chi-squared distribution with our degrees of freedom of k minus 1. Therefore, the p-value associated with the computed test statistic value is the area to the right of chi-squared under the degrees of freedom k minus 1 chi-squared curve. So what assumptions do we have to have? Well, first, our observed cell counts are based on a random sample. And second, that the sample size is large enough as long as every expected cell count is at least 5. So what are some facts about our chi-squared distributions? Well, different degrees of freedom have different curves. Notice here that we have a degrees of freedom of 3. All of our chi-squared curves are going to be skewed to the right, as we see here. But if we take our degrees of freedom and we move that, let's say degrees of freedom of 5, we're going to see how that changes our curve. And it's still skewed right, but not quite as steep. For degrees of freedom of 10, same thing happens. So notice that as our degrees of freedom increases, the chi-squared curve shifts towards the right and becomes more like a normal curve. Let's look at an example. So a common urban legend is that more babies than expected are born during certain phases of the lunar cycle, especially near the full moon. So the table below shows the number of days in the 8 lunar phases with the number of births in each phase for 24 lunar cycles. There are 8 phases, so our K is going to equal 8. So we would let P sub 1 be the proportion of births that occur during the new moon. P sub 2 is the proportion of births that occur during the waxing crescent moon. P sub 3 is the proportion of births that occur during the first quarter moon. P sub 4 are the proportion of births that occur during the waxing gibbous moon. P sub 5 is going to be proportions of births that occur during the full moon. P sub 6 would be the proportions of births that occur during the waning gibbous moon. P sub 7 is the proportions of births that occur during the last quarter moon. And our P sub 8 would be the proportions of births that occur during the waning crescent moon. Now there are a total of 699 days in the 24 lunar cycles. So if there is no relationship between the number of births and the lunar phase, then the expected proportions equal the number of days in each phase out of the total number of days, as we see here. Remember, we got these values from our table that we used to calculate these. So what would our hypothesis statements look like? It would be that our H sub O, or our null hypothesis, is that our P1, P2, P3, all the way to P8 equal these values. And our alternative hypothesis would be that our null hypothesis is not true. So let's go ahead and put up our hypotheses. Now, there is a total of 222,784 births in the sample. If there is no relationship between the number of births and lunar phase, then the expected counts for each category would equal n times our hypothesized proportion. So here we see our lunar phases, and now we have our observed number of births, and here we have our expected number of births. So from here, how would we now calculate our test statistic? We would subtract our observed from our expected and square it, and then divide it by our expected, and do that for each phase, and then add those up. And that would give us that our chi squared is 6.557. That's going to give us a p-value that is greater than 0.10 and degrees of freedom of 7, looking at our alpha as 0.05. Now, how do we get greater than 0.1? Well, the chi-squared test statistic is smaller than the smallest entry in the degrees of freedom equals 7 column of our appendix table 8. So because our p-value is greater than our alpha, we fail to reject our null hypothesis. So there is not sufficient evidence to conclude that lunar phases and number of births are related. So what type of error could we have made? That's right, a type 2 error.